Okay, good morning, dear students. Today we are going to talk about local buckling. In general, in structural engineering, in the construction, the buckling is a sudden change uh, in shape, so deformation of some structural component under the load. So such as bowing of the column under the compression or the wrinkling of a plate under the shear. If structure is subjected to gradually increasing load, so when the load reaches actually, so the critical level, a member may suddenly change the shape and the structure and the components is said to have buckling. Classification of the sections for the buckling. Buckling in general may occur when through the stress in the metal construction developed the structure um, are well below those needed to cause failure in the material or which the structure is composed. Further loading to the construction may cause significant and somewhat unpredictable deformations. So possible leading to complete the loss of members' load carrying capacity. However, its deformations that occur after the buckling do not cause the complete collapse of all member. So at all structure, column, beam, so there is still construction. But in the same time, the member will actually continue the support the load that um, cause it to buckle. So, but if the buckled member is part of a large assemblage of components such as building or for example, any applied load. So in general, it will be difficult to construction to carrying the load, even the buckling state. A key factor that can limit the ductility of the steel member is the development and the growth of the local buckling. Consequently, for members that are expected to see significant and elastic action and exhibit huge ductility, the special seismic provisions specify a very respective with the thicknesses thicknesses limits actually the seismic the local buckling is delayed until adequate ductility is achieved. So the section which satisfies very restrictive with thickness limits can call it seismically compact action. So controlling the local buckling, so one of the most critical factors for achieving ductile response of metal constructions. And the next slides will show some examples of the um, presenting in the constructions local buckling. So on the picture you see the beam section. So this beam section was seismically compact. Note that being seismically compact does not actually mean the local buckling is prevented. So it's not actually possible to prevent local buckling in general. Local buckling can be only local buckling can only be delayed. So this specimen developed the full plastic flexural strength of the beam and maintains the strength through the large inelastic deformation. So like specimen development, very large ductility. Before local buckling developed and the flexural resistance of the beam began to degrade. So the ductility of the beam was therefore ultimately limited by the local buckling. So mm, however, using the seismically compact section, beam developed very large ductility before it lose the strength of local buckling. So here is another example of the load buckling, and in this case, in an eccentrically braced frame, so EBF, eccentrically braced frame, um, with the size of the wide flange beam W16 to 36 section of the beam. The subject were subject to serve cyclic and elastic load in laboratory test. So under some laboratory forces, loads. So the local flange and the web buckling is clearly visible at the at the ends of the members. So you can see it. The link section is also seismically compact. As with the moment frame beam, the previous slide satisfying seismic compact limits, so does not actually prevent the local buckling. Because this link section was seismically compact and developed very large and elastic deformations before ultimately failing was found by the local buckling, like you see on the picture of the beam. Next, so the theory of the behavior of the columns in the past was investigated by the scientist Leonard Euler. So in the 18th century. So, and some main facts with regard to the load-bearing ability of the slender columns. So it is the elasticity of material of the column and not actually the compressive strength of the column and determines the column buckling loading. The buckling load is directly proportional to the second moment of area of the cross section of the cross section. Boundary conditions have considerable effect on the critical load slender column. So boundary conditions, it is connection type. So how connect connected the columns, slender columns. So the boundary conditions determine the mode of bending of the column and the distance between inflection points of the displacement curve of deflected column. So um, inflection points in the inflection shape of the column are the points which curvature of the column change sign and also the points in which the uh, columns internal bending moments of the column are equal to 0. So the closer the inflection points, the greater resulting actual load capacity, so buckling load to the column. So next one. So sub, when the beam is simply supported, so so when the simply supported beam is loaded in bending, so the top side is compression, but the bottom side is a tension. So if the beam is not supported at the lateral direction, so it's perpendicular to the plane of the bending, and the flexural loads are increased to a critical limit, the beam will experience a lateral deflection of the compression flange as a buckles locally. So the lateral deflection of the compression flange is restrained by the beam webs and the tension flange. But for open section, the twisting mode is more flexible. So hence at the beam both twist and deflected laterally failure. So this processes, this mode well known like lateral torsional buckling. So wide flange section with a higher lateral bending stiffness, the deflection of the mode will mostly twisting in the torsion. So in narrow flange section, bending um, the bending stiffness is low in the column deflection and will be closer to the lateral buckling deflection mode. Uh, next one, the column splices. So column to column connection usually determined by the change in section. in general, change is made very at every second floor level. So where a shop or field splice is located. So from an erection viewpoint, as well as fabrication and the shipment. So splices at every third floor may be more economical, maybe more efficiency because of the reduced number of the pieces, pieces to handle. So then less number of the splices, then less pieces of material we need. So this actually advantage is partly offset by extra weight of column material because column size is determined by loads. So on the lowest story of each tier. So the bending being an exit of the section for story or two above. So splice is actually located just above the beam connection. So usually about two, um, maybe one meter to 1 2 meter above the floor, because column stress is transferred from the column from column to column by bearing. So in the splice plates are nominal size um, which show with the need for safe erection from the viewpoint of the moment resistant conventional column displays develops perhaps about 20 to 25% of moment capacity of the column. Next one. So partial joint penetration, so PGP groove welds, so may not perform well when the loaded is tension. So the weld portion of the column flange acts as a as H crack to the root of the weld and may initiate a may initiate the brittle fracture. So one side of the partial joint penetration weld shown on this figure. And so it may particularly prone the fracture if there will be torsional load. Actually, this potential poor behavior of the partial joint penetration in tension is why all these requirements in this section require that strength of the strength of the partial joint penetration should be doubled, as less as doubled. So note that the special moment frames and intermediate moment frames so covered actually in the other will be covered by us in the other presentations. So do not permit the partial joint penetration groove welds to the column splice because potential unneedable to the fracture. So these systems, if groove welds are used at the column splices, so they must be completely fooled by joint penetration, so by the groove welds. Groove welds. So groove welds are most of all used in the column splices. So it's not necessary to provide the believe transmission in the thicker flange. So as shown in the previous slides. So providing providing the needable level of transition may reduce the strength concentration at the groove welds and may be beneficial even it not required. So according to the various codes, norms, the fabricator finishes with the structural steel. So to be erected by the sawmills, the field balls require fastening the steel. So the fat fabricator, however, does not furnish the following items. So it's a specified like invitation to beat. So there are bolts, drift pins, temporary cables, electrodes, and zinc leveling plates to column bases. So the code actually defines the all erection principle and the practice. For example, erector does not paint field bolt heads and nuts, field welds, or some abrasion if there are someone in the shop code. So perform any other field painting unless required in the specification. So next one, it's a column web splice. Web splices can be bolted or can be welded. So using the pair of splice plates in the web as known in the figure. So may be beneficial the event of the column flange splices fail. So when the difference in the column size is pronounced, the practice is to use horizontal bearing plate as shown on the figure 7.56. So these plates known known like butt plates. So they may be attached at the upper shaft because the plate is lower, so may interfere with the erection of the beams frame into the column web. Finally, this section states splice with groove welds, with fillet welds, should be located at the least. So the connection from beam to column connection, and it's move uh, away from the highest moment region of the column, and also typically locates in the splice at the convenient spot for fabrication by the iron workers in the field in the place of erection. So also this requirement applies only welded or fillet welds are used. It seems the product to follow for any type of the splices. And the last slide for today is the example of column splice. From the picture is made from the side. So for today is all information. If you have question, I will be able to answer it. Actually, we have at least about 10 minutes.
We haven't got questions.
Okay, let's read your questions. So there was some problem with the microphone, but not that's not question. Okay.